Okay, this is a digital circuit class. And we're finishing off chapter, if I can spell chapter 5. And we're going to do it looking at the multi-sim exercises. We're going to look at E5-1 first. E5-1. And I'm not sure how we're going to get to E5-1. I think we click here, right? Yeah, we click there. And problems, examples, problems. Yeah, problems. Version 9 because we're 10, 5, chapter 5. And we're E5, 1A or 1B. Okay, so we're going to open E5-1. This is an illustration of combination logic similar to figure whatever. The circuit is an automobile system. You turn it on. Okay, write the Boolean equation at B. Test the Boolean equation by moving the appropriate switches. Right? And the equation in the circuit can be reduced to a simpler form. Do that. What is the reduced form? Okay, so I've got, can I write on this? I can't write on this. Okay, no problem. I can do that. Alright, so I've got K, D, I've got H, D, I've got B is equal to H, D, or KD. Is that not what I have? Yeah, that's what I have. And then I can reduce that. How can I reduce that? H or K D. That doesn't seem like too much of a reduction. But I suppose I could do that. So I could have H, K going through an OR gate. And then I could have D going through an AND gate, and that would be B. And before I had 1, 2, 3 gates, and now I've got 1, 2 gates, so I guess I've reduced it. Okay, next problem, E5-4. E5-4 says open 5-3B. 5-3B. Okay, this looks interesting. What is the Boolean equation at X? Okay, so I've got AB. I got BC, I got AB or BC. So X is going to be AB. This is AB, BC. And X is going to be A, B, C, or AC. Not AC. BC. A, B, C, or BC. Okay, so that's the equation. Create a truth table using the logic converter. How many different input combinations produce a 1? Okay. So there's the logic converter. And we're going to go and hook up that guy to the outside, like that. I certainly hope that they're connected. Yes, they are connected. Okay, that's good. All right. Then I'm going to turn this on. Oh, I don't have to turn it on. I'm going to go from the gates to the truth table. 1, 2, 3, 4, 5, 6 of them are 1. 6 are 1s. Using the logic converter, find the simplified equation for x. Well, without using it, I can find it for x, right? It's BC. But I'm supposed to do it using the logic converter. Okay, so I'm going to go and take the truth table and change it to a Boolean expression, and then I'm going to simplify it, and I get BC. All right, so the logic converter did in fact do what it was supposed to do. Convert the logic. All right, next guy is 5, 9. Okay, 5, 9, I'm supposed to open 5, 4A. 5, 4A. Now, why didn't they label these guys right anyway? We can't open, what do you mean we can't open it? That's on, this is off. Why can't I get rid of these guys? Got rid of him, got rid of him. Has been not, no, I don't want to save it. All right. Looking for 5A. Okay, there we go. All right, now we're open. We're supposed to create a truth table using the logic converter. How many produce a 1? All right. Again, we're just going to hook up the logic converter. Notice that I don't have to turn this guy on to make the logic converter work. And 2 of them. So we'll come back to, yeah, we'll come back to there. Do a picture of that guy. And so we say E5, 9A, 2. All right, so 2 of them give up. Use the logic converter to simplify the equation. All right, so I'm going to go make the Boolean equation. And 5, 9.
Didn't you just do what was 5, 4?
It says E5, 9. It says I'm supposed to open the file marked section 5, 4A. See where it says that in your book? So the multisim files are not numbered the same as the exercises. So where E59 is, load the circuit section 5.4a.
Okay, so for like on the syllabus it says E54 and E59, they're both the same?
No, they're not the same.
What was E54?
E54 was the one we just did. E54, we're supposed to open section 5.3 Bravo.
No, but the A, B, A and B, and the A or B are both knotted, correct? That's what I'm reading, the apostrophe at the
Yeah,
end.
the apostrophe, yeah. The apostrophe at the end, right. So anyway, I'm simplifying it, and I get B naught, C naught. So the file that I open is different than the problem number that I'm on.
I didn't hear, I thought.
So if I go back, see there's the file that has E5, 4, and there's 6 ones. 1, 2, 3, 4, 5, 6.
Okay, yeah, I put E53.
Yeah. All right, this is E59B. And it says the simplified form is B naught C naught. All right, now 524 says open section 5.4J. Okay, so now I'm supposed to open 5.4J. Multisim cannot open the file while there is an active monodiagram section, blah, blah, blah. Please close the, well, whatever. All right, so we're going to close that. We're going to close this. I'm going to try it again. All right, so 5J. We'll go and capture this for a moment. And this is E524. And what does it say? It says we have quad nands. On a separate piece of paper, write the Boolean equation for the circuit shown. Simplify the equation. Double-click on the logic analyzer. Turn on the power. Observe the waveform. And which gates are bad. Okay, so that's the plan. All right, so that's the plan. I look at this.
Doug, take this one slow.
All right, so I'm looking at it. Okay, and there it is. So I've got B going through a NAND. So that's, that was cool. Was that cool or what? So I've got B naught there. And here I've got A naught there. And then coming out, I've got A naught, B naught, naughted. And now I'm supposed to simplify that. So it's A double naught or B double naught. A or B would be my simplified equation. So I've gone and found the equation. I've simplified the equation. Now I'm going to see whether or not it's working. All right, so that's a different issue. So we'll turn this guy on. And this guy is going to show that. I'm going to turn this guy on, see what it's going to do. So he's going to put in a 1, 2, 3, 4, 5, 6, 7, and then quit, is what he's going to do. All right, so then he's going to do it in hexadecimal. That's fine. All right, so we turn on, boom, and we see something that looks like that. All right, now, the issue is the green guy on the bottom is the output waveform. Okay, so that's the issue. And I'm going to go and capture that for a moment. Okay, so I'm there. Now I expect to see A or B as my output waveform, right? And if I see A or B, then what I should have seen, let's see if anything, maybe red will write. Okay, what I should have seen is I'm low, and then I'm high, and then I stay high, and then I stay high, and then I go low, and then I go high, and I stay high, and I'm high all the way. So that's what I'm supposed to be seeing, but I'm not seeing it. Using the logic, observe the waveform. Are they what you expect? No. No, I don't expect this. But that's what I have. Which one of the gates is bad? Okay, which one is bad? Well, wait a minute. Back to looking at this guy. All right, we're gonna erase that because we have a problem. And the problem is I've got A coming there. So that's A. I got B coming there. C is the green guy that doesn't go anywhere. So that green guy I'm not going to use. Back to my picture. So the top green guy is not relevant to the problem. So if the top green guy is not relevant to the problem, what I should see is that I should see that whenever it's A or B.
Didn't it go high?
Oh, it's got to go
There.
high across there too,
Yeah.
yeah. So it's A or B, and it's going to look like that. So now the issue is which gate
Still not
is,
what you expected.
huh?
Still not what you expected though, right?
Yeah, it's still not what I expected. No, I don't expect that. I have a problem right there. I got a problem there. So what is causing that? And that's being caused by the B guy.
So it's not C.
So it's the blue line, and the blue line is connected to,
Blue A?
blue line is the B guy.
Oh, B.
So the problem is this gate. Okay, that's the problem. So I'm going to go and I'm going to turn this off for a moment. And I'm going to go get a probe. And I'm going to put one there. I'm going to put a probe, and I'm going to put one there. I'm going to look at what's going in and what's coming out. I'm going to turn this guy on. And it looks like I need to come back up to there. So I do it again. I set the cursor. Okay, so we're going to be there. I'm going to turn it back on. And notice that this guy blinked on and off, but this guy never did anything. He was off the whole time. Notice that? I'm going to. Should I do it again? I'm going to do it one more time. And so we're going to come back up to there. We're going to change the frequency, and we'll change it to 100 hertz. Now 100 hertz, and maybe it'll slow down some. That didn't change at all. Oh.
Try to change your meter.
Yeah, I've got to change the internal. I have to change something else. Well, I won't bother. Did you see it that time? You did?
Yes.
All right.
Back.
Well, I'll do it one more time. You're gonna see this guy blinking off, but this guy not turning on. Okay, and that's the problem. The problem is that gate doesn't work. So if I go, and that's why they gave me the second gate. So if I go and hook this guy.
Doug, if you went back to your graph, the green line and the red line were identical anyway, so you knew that was a good.
I don't think they're identical.
They were in your last graph.
I'm having trouble controlling myself here. All right, so I'm gonna get rid of that guy and hook up the other guy. We're gonna come back here. So there's the green line. It's going up and down like that. How is that identical to anything else?
No, look at the bit 6 and 7. They're identical.
6, right? Exactly. Yeah, that's yeah.
And so obviously that's the one that's running properly.
The red line is running properly. The blue line is not. I agree with your analysis. All right, now that we've changed the diagram, we'll go back up to the top. And we're back up to the top. We're going to turn it on. And nothing happened. Thank you very much. Set the cursor. Okay, so the cursor is set. Boom. They both blink that time? My problem is my logic analyzer is not set right for some reason. Oh, yeah. Yeah. No one saw that, right? Yeah, no one saw it. All right. Okay. So now we're getting what we expect. Okay, so we fixed the one that was wrong. We're getting what we expect. And delete the bad gate, replace it, and validate proper operation. Okay, so that's exactly what we did. We fixed the bad gate, and we made sure that it works. Okay. Get rid of that. Get rid of that. Get rid of that. Don't get rid of this one. Okay, so now we're in chapter 6. And oh yeah, cool. So if I have A, B, and I have 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, yeah, 1, 0, 1, 1. Okay, and I got that. And I've got A naught, 1, 1, 0, 0. And I've got B naught, 1, 0, 1, 0. And I've got A, B, 0, 0, 0, 1. And I got A or B. And I got 0, 1, 1, 0. All right. Now,
That's one. That's a one for the last one. 0, 1, 1, 1.
Yeah, 0, 1, 1, 1. All right. Now, those are the things that I have, right? But if I look at that, I say, well, there's more possibilities than that. I could have a,
B naught.
huh?
You can have A B naught, A naught B.
I could have a, yeah, I could have a B naughted. I could do that, right? 1, 1, 1, 0. I can have A or B naughted. 1, 0, 0, 0. All right, so I've got that. Now, there's other possibilities. I could have a, I got an inverter, I could have an OR, I could have a B, I could have an OR, I got and, or, nan, nor, or I could have a Doug gate. Okay, so I'm going to have a Doug gate. And the Doug gate is going to be 1, 1, 1, 0. Oh, wait a minute, we already have that one. Can't have that one. So we're going to have a 1, 0, 1, 0. There we go. The Doug gate.
Yep, B naught.
Oh, bummer. Okay, so I'm going to have a 0, 0, 1, 1. Oh, 0, 0, 1, 0? Okay, there we go. 0, 0, 1 gate. So so I'll have that gate. All right. And then we'll have a Ryan gate. And we'll have a 0, 1, 0, 0. Now we got a Ryan gate. So there are possibilities of gates with our names on it here, that we could get to. Huh?
This is what that Karnoff guy saw?
No, he didn't see this at all. But if we go and we say, well, now that we've agreed that there are possibilities, we could have A, B, 0, 0, 0, 1, 1, 0, 1, 1. We could have a gate that does 1, 0, 0, 1. Or we could have a gate that goes 0, 1, 1, 0. We could have those two gates. And if we did, because they're not used yet.
And this is simply because you're adding the nots.
This is simply because I have ones and zeros that I can play with, right? So if I have two guys of ones and zeros, these guys can be how many combinations? I can have 0, 0, 0, 1, 1, 0, 1, 1, right? But I have 1, 2, 3, 4 of them. 4 times 4 is 16 possible gates I could have there. And I'm not using it. I'm only using 1, 2, 3, 4, 5, 6, 7, 8 if we count Doug and Ryan. 9, 10 if we count these guys. So this guy is going to be an exclusive OR. And we're going to use a symbol like that for exclusive OR. So that'd be A, exclusive OR B, which means that if it's one or the other, it's true. But if it's both of them, it's false. And if it's only one, if it's all zeros, it's false. Or I can have, this guy's going to be an exclusive NOR. We're going to have a symbol that looks like that. And I'm going to have A, exclusive NOR B, if I could write it. And that's going to, now if they're both zeros, I get 1. If they're both ones, I get 1. Okay, so it's the opposite of the exclusive OR. All right, so I got a exclusive OR. It's going to look like this. A, B, A, exclusive OR B. And I've got an exclusive NOR. And it's going to look like this. And it's going to be A, exclusive, exclusive NOR B. I'll make it better. That was pretty bad. And
that extra line by the AB is basically like just little circles where your wires type. You're inverting it prior to going through the OR.
There's no OR. No, there's no inversion. This guy down here, is that what you're talking about? That's the not.
Well, either one of them.
No, that's
the double line.
No, that has nothing to do with knotting anything. That has to do with a symbol for the exclusive NOR. Or the symbol for the exclusive OR. All right, and they say, well, that's interesting. Why would I care? And so now we're going to switch gears here. I got, I'm going to add. I'm going to add a binary. Okay, so I got 0, 0, I get 0. I have 0, 1, I get 1. I get 1, 1, and I get 1. No, I don't. I have 1, 0, and I get 1. I get 1, 1, and I get 0 with a carry. All right. So if I'm doing a binary add, I'm taking A, B, and I'm sending it through an exclusive OR to get the summation. And I'm taking A, B, an AND gate, and I'm sending that over here to my carry. And I'll do that one more time because that's pretty silly. I'm going to go and take A, B, into an and that's going to be my carry. So when I'm adding in binary, I'm using an exclusive OR to find the summation, and I'm using a AND gate to find the carry bit. Okay. Well,
why are the two ones adding up to 0 now? I mean, what?
Well, because it's a carry of 1. A 1, 1 would be a 0, a 1, 0. It's a 2. And that's how I
Okay,
make the
well, you
2.
could have shown that before.
Yeah.
Now
Well, I
maybe
can't
some
put
ways
it
to zero.
can't put it there. So now I get my summation by using an exclusive OR, and I get my carry by using an AND. And then, yeah. Now, let's look at this one more time here. We have A exclusive OR B. It has a truth table, ABX 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0. So this is going to be A naught B or A B naught. A naught B, right there. A
That should be a 1. 1, 0, 1, shouldn't it?
yeah, that's a 1, yeah. That's that guy there. Now I'm going to do it again. And I'm going to have A exclusive NOR B. I have a truth table. AB 0, 0, 1, 0, 1, 1, 0, 1, 1. I've got an output X 1, 0, 0, 1. This is A naught, B naught, or AB. Okay, one more time. A, B, C. So I have A, B, C going in through 3 inputs to an exclusive OR. X is going to be A naught, B naught,
What do you need A naught plus 4?
we're going to do this one because it's easier. A naught, B naught, C naught, or A, B, C. There we go. If I do it to 3 of them, A, B, C, and I do that, then I have to have everybody but these. So I have A naught, B, C, or A naught, B naught, C, or A, B naught, C, or blah, 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 all the rest of them, yeah. So there's a huge number that I could have, but I can't have the guy that's all zeros and all ones. That wouldn't be allowed. All right, I'm turning the page.
For exclusive, we could show the ones that wouldn't work.
For the exclusive NOR, I'm showing this guy and that guy. These are the guys that are going to be 1. If it's all 0, it's going to be a 1. If it's all 1, it's going to be a 1. Okay? For the exclusive OR, there's too many of them to show, so I'm not showing them all, but it's everyone except this one.
It's 3 plus 2 plus 1, it's going to be 6.
So if I go and I do it logically, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay? I don't use that one, and I don't use this one. So A naught, B naught, C, or A naught, B, C naught, or A naught, B, C, or A, B naught, C naught, or A, B naught, C, or A, B, C naught. There, now I got them all. There. So that would be my 3 input exclusive NOR. And I'll try to do it with 8 or something like that.
That's a trifecta box at the dog track.
Is that what that is? Okay.
So exclusive.
Yeah. Okay. So now we come down to reality. Where's reality? where reality is going to hit the road, I got a thing called a computer. What do computers do? They collect dust, right? Yeah, basically they collect dust. Anyway, computers have a CPU. They have an arithmetic unit. They have random access memory. They have read-only memory. And basically what they do is they move data on buses from one place to the other. And then they execute some code, right? So I got this random access memory, and I'm going to go and I'm going to move the random access memory into the CPU. Now, I've got 16 bits of data moving into the CPU. Do I want to know that it's correct? Okay, what makes me think it's correct? It's supposed to be. Yeah, it can't possibly be wrong, right? So we found out very early in our computer science days that back in the 40s, talking about back in the 40s, that if I'm going to move data across the data bus and addresses across the address bus, I have to have some assurity that what I'm getting is correct. So what we did is we took our 8 bits of data and we added another bit to that data string, and we called it the checksum. And we're SUM, right? And we called it the parity bit, Parity. And now our computer can be odd parity or it can be even parity. We have to decide which one, and we build it so it is. And whenever we take a piece of data out of the random access data memory, we put a parity bit on it. And then with that parity bit, when it gets to the CPU decides, is the data correct? If the parity bit's correct, then we accept it and we execute the command. If it's not correct, then we ask for it again. And normally we'll ask for it 1,000 times before we go into fault. Well, 1,000 times is going to happen pretty quick. 1 megahertz, that's going to happen pretty quick, quicker than we can think about it. All right, so how do I do that? Well, if I have some data 11101110, and I've got a parity bit, and I've got 00101011, and I add a parity bit, and I've got 110111. 1, 2, 3, 4. Too many. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And I'm doing odd parity. Okay. So what I'm going to do is I'm going to add up the bits, and they're going to come to an odd number. 1, 2, 3, 4, 5, 6. Parity bit 1. 1, 2, 3, 4. Parity bit 1. 1, 2, 3, 4, 5, 6, 7, parity bit 0. That's what I'm going to do. If I'm going to do even parity, and this is all done in hardware. This is not done in software. This is done in the hardware. 1, 2, 3, 4, 5, 6. Even parity, I'd be a 0. 1, 2, 3, 4. Even parity 0, 1, 2, 3, 4, 5, 6, 7. Even parity 1. Now I have 8. Okay? And then I say, well, if I'm going to do that, I'm going to go and make sure my data is correct by adding a parity bit, which right now, all your desktops, all your laptops, they do it. You don't care. They're just doing it. You're not doing it when you talk on the phone and sending the data that way. You're not doing it that way. You're doing something else. You're encrypting the data, but you don't encrypt data going to and from your address bus or your data bus. Clearly, I need to have a a parity generator, right? Parity generator. And I need a parity checker. And because I need both, I need to generate the parity bit when I leave random access memory, and then I got to go and check it when I get it in the CPU. So that's the whole thing. So how am I going to do that?
How are you gonna keep it cool? It sounds like it's gonna be doing some work.
It is. Well, think about your random access memory for a moment. How long does it take for it to go away if I turn off power?
Right away.
Okay, yeah, right away. Like, right away, yeah. So, your random access memory, this is an aside, is 1,000 times a second is being refreshed. So the circuitry is reading that 1 or 0 and rewriting it 1,000 times a second into every memory location of random access memory in order for it to be there when you go to get it. Okay, you're refreshing the memory. And back in the good old days when we had the 8088s and the 286s, those were all individual chips doing that on your motherboard. So your motherboard had 100 chips sitting on it. Some of them were random access memory. A portion of the board was the refreshing of the memory going on. And it was going on independent of the processor. It had its own timer on the board, and it was doing it on its own. Now it's all done internally to the CPU, and we don't mess with it electronically anymore. Okay, so if I go and have, we'll go with 4 bits. I have bit 0, 1, 2, and 3. And I send 2 of them through an exclusive OR. And I send 2 more through an exclusive OR. And then I send them both through another exclusive OR. Then I have an even parity bit. And if I do the same thing over again, and I send them through an exclusive OR, and I send the other 2 guys through another exclusive OR, and then I send them through an exclusive NOR, then I have an odd parity bit. And I can do this with 8, I can do this with 16, I can do this with 34. I just keep on adding to my circuit. All right, so we say, well, I don't believe it. Okay, so I got a 1, 0, 1, 0. Okay, I get a 1 there, I get a 1 there, I got a 0 there, 1, 2, even parity bit 0. I got a 1, 1, 1, 1. 1 and 1 gives me a 0. 1 and 1 gives me a 0. 0 and 0 gives me a 1. Say 0, 0 gives me a 1. Boom. Odd parity bit. 1, 2, 3, 4, 1 more for 5.
All right, yeah. Isn't that not back to 0?
The truth table. The truth table for the exclusive NOR is 0, 0 gives you a 1. 0, 1 gives you a 0. 1, 0 gives you a 0. 1, 1 gives you a 1. So 2 zeros coming in gives you a 1 going out.
Yeah, but then
you have not
you have not.
No.
You got this little circle at the end of it.
But see, that little circle is nodding this guy. That's nodding the exclusive OR. The truth table for the exclusive OR is 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. I did nod it. That's why it's a 1.
Yeah, but if your 2 zeros come through, produce a 1, that gets knotted.
No, the output's a 1. The 2 zeros give me an output of 1. There's no nodding about it.
Well, maybe you got the little circle.
This is one thing.
Yeah.
This isn't two things.
Okay.
So this is one thing over here. The 2 zeros give me a 0. There's a knot there. It becomes a 1. That's the 1. Okay, you can think about it that way. But the exclusive NOR has its own truth table.
Oh, okay, okay, I got that.
It's not, that knot is not in addition to the truth table.
I got that.
It is the truth
It's its
table.
own thing completely.
That's right.
Yeah.
It's one thing. It's not two things.
Why did we even make these?
Because we had to, because our first computers would transmit friggin' data at the awesome 1K rate and get it wrong. And our computers would crash, and they did it frequently. And so we had to come up with a way to know that the data was right, because a 16-bit command to add is different than a 16-bit command with 1 bit wrong. And it was constantly sending the wrong thing. And yeah, we had to deal with that.
I guess I'm not seeing it, but on the right, like the zeros up top are 1s, they go into it, and then because it's an OR, on the part you got circled, on the right.
Yeah, well, these are exclusive NORs, exclusive ORs. I don't have that other line there, so I should have put that other line in. So the 0, 1 becomes a 1. The 0, 1 becomes a 1. The 1, 1 becomes a 0.
And then because you
But
got
then-
the little circle, it reverses from the second.
Apparently it's just one
But then on the
component.
second one, if they would have went in 1s.
1, 1 becomes a,
That's a single component acting as a NOR.
1, 1 becomes a 0. 1, 1 becomes a 0. The 0, 0 becomes a 1.
Because it's a NOR, not a NOR, right?
But then wouldn't
Because
1,
it's
1
it's an exclusive NOR.
NOR, not.
It's a different animal. Well, if I can make the parity bit, I'm going to have to check the parity bit, right? So, all right. So I'm going to take the parity bit,
It's not exciting.
and I'm going to get 2 exclusive ORs. Four pieces of data. Do it again. And then bring the parity bit down and do it one more time. And this is for even parity. So I just I sent some piece of data 0, 1, 0, 1. And I sent, and it's even parity, so the parity bit should be a 0, but for some reason my parity bit's a 1. The 0, 1 becomes a 1, the 0, 1 becomes a 1, the 1, 1 becomes a 0, the 0, 1 becomes a 1, and a 1 means there's an error. Okay, I do it again, and I'm gonna have a parity bit of 0. I have a 1, 0. I got a 1, 0. I get a 1. I get a 1. I get a 0. I've got a 0, 0. 0, 0 gives me a 0, which means I am okay. So that's how I do my even parity bit. My checker, how I check it. Now, how do I check the odd parity bit? I do the same thing, but this time this becomes an exclusive NOR. Okay? I can have my parity checker, and my parity generator can be a chip all to itself. So I can have all those guys on the same chip, do whatever it is it does. So I look on page 344 and 345, and I see an 8-bit, I'm generating an 8-bit parity guy. And I'm doing it, and I'm going the other way, and I'm converting it back. You know, just something we had to do. That might be all there is to this chapter. Yeah, it is. That's all there is to this chapter. So now it's time to work some problems, which I know that everybody would just love, right? Problem 6.1. Describe in words the operation of an exclusive OR gate.
Oh, we gotta go to 6.3.
Oh, we're not doing 6.1? Oh, bummer. I gotta turn the page. All right. So I'm looking at 6.3. Complete the timing diagram. Okay. So I got an A, I got a B. My A goes up and down, up and down, up and down, 4 times, up and down. All right. And then my B starts low, goes high, goes low, goes high, goes low. I got that? And then I need an X and a Y. Okay, so I've got A, B, exclusive OR, X. And I got A, B, exclusive NOR, Y. Okay, so now I'm going to do the X guy. When they're both 0, I'm at 0. When one of them is high, I'm high. Something might happen there called a glitch. When they're both high, I'm going to go low. I'm going to stay low. One's high, I'm going to go high. I'm probably going to do something weird there in the nanosecond time frame. When they're both high, I'm going to go low, and I'm going to stay low. Okay. Now, what color? We'll use black. Okay. Exclusive NOR. They're both low, so I'm going to be high. One is high, so I go low. Something may happen there. Something may happen there. They're both low. Well, when they're both high, I have to go high. So let's get rid of this. Okay, they're both high, so I have to go high again. They're both low, so I have to be high. One is down. One is down. They're both up. They're both down. So something might or may not happen on those transitions. The gates operate in the nanosecond time frames, 5 nanoseconds. So if we have an oscilloscope that's operating in kilohertz time frames or in megahertz time frames, we're not going to see that transition at all. It won't be there. So we'll get rid of it. But if we have something that can see in the nanosecond time frame, it's going to see those transitions as the digital circuit changes from high to low. Any questions about that?
Are those NANDs or NORs? Or a NAND and a NOR? Or
One's an exclusive OR,
exclusive?
the X. The other one's an exclusive NOR the Y. Exclusive or exclusive NOR. So for the exclusive NOR, they both have to be low to be high. Or they both have to be high to be high. For the exclusive OR, only one of them, if only one of them is high, it'll be high. If they're both high or if they're both zero, it's going to be low. Okay, what are we doing? 6-4? 6-4. Oh, just plain wonderful. Write the Boolean equation, simplify the Boolean equation, determine if they are functions or neither. Okay, so this will be fun. A, B. Yeah, I got A and B right. All right, so I got that guy, and I got this guy, and I got that guy. All right, so I've got A, B, knotted. A or B. I got A, B, knotted. A or B, knotted. Okay, so I've done step one. I've written the Boolean. Now I got to simplify the Boolean. A, B, double knot, or A or B knotted. A, B, or A knot, B knot. Okay, so that's a simplified form. And we can say that that is an exclusive NOR. Because that's the definition for the exclusive NOR. A, B, or A naught, B naught. Okay, moving on to the B guy. Got A, I've got B, I've got an O, I got an AND, I got a NOR, I got an OR. A, B, B. All right. A, B, A or B, knotted. A, B, or A and B, knotted. A, B, or A naught, B naught, exclusive NOR. Okay, so we got two in a row. So we'll do a little bit of a side. If I'm a plumber, are those pipes connected? Okay. Okay, so here we got plumber. P-L-U-M-E-R. I got a plumber. And over here I've got an electrician. E-L-E-C-T-R-I-C-A-N. Okay, so here I'm a plumber and connected. And so the answer is, if I'm a plumber, the answer is yes, they are connected. If I'm an electrician, are they connected?
No.
The answer is no, they are not connected. Okay, if I'm a plumber and I have something like that, or if I'm an electrician and I have something like that, then now I'm not connected here, and yes, I am connected there.
Okay. Just got so
So if I'm running wires and I do that, None of them are connected. If I'm running wires and I do that, and I put a dot there, all three are connected there. So it's just a matter of, am I looking at a schematic that's plumbing, or am I looking at a schematic that is wire? Wires use dots. All right, so that was just an aside, just in case you wanted to be confused. Okay, so Charlie, I've got one of those guys. I'm knotting the inputs to one of these guys, and then I'm re-knotting them again, going into that guy. A, B, A, B. All right, so I got A, B, A naught, B naught, A, B knotted, A naught, B naught, knotted. All right, so I got the Boolean. Now I get to simplify it. A naught, B naught, A double naught, or B double naught. Okay, A naught or B naught, A or B. A naught A, or A naught B, or A, B naught, or B naught B. Now, A naught is 0. B naught is 0. So I've got left over is A naught B or A, B naught, which is the definition of an exclusive OR. So that circuit is an exclusive OR circuit. Now, why I would want to do that, why I'd want to spend the money on those particular chips to do that, I have no idea. Delta. A, B, okay, so I've got something looks like that, something looks like that, something looks like that. Hope this guy's a neither. A, B, A, B. All right, I got A, B knotted, A or B knotted, A, B knotted, or A or B knotted, the whole thing knotted. All right, see, what am I going to do about that? All right, so I got A, B, double knot, and A or B, double knot. A, B, A or B, AB. Aha, I was right, neither. It's neither an exclusive NOR or an exclusive OR. 6-12. Figure 612 shows another design. Oh, I got to do 6-6? Bummer. How did I miss 6-6? Easy, huh? Oh, design an exclusive NOR gate constructed with all NANDs. Okay, that should be simple, right? Okay, so I want an exclusive NOR. An exclusive NOR is A, B, or A naught, B naught. Okay, so that's what it is. So, and I'm using only NORs, only NORs. Okay, so 6, only NANDs. Okay, only NANDs. All right, so I got A, B. I bring it into a NAND, and I invert it. Alright, so there's my AB sitting right there. I need an A naught, and the way I get that is doing that. And I need a B naught, and the way I get that is doing that. Alright, so now I've got an A naught there, and I got a B naught here. I want to AND them together. So I'm going to go and AND them together like that. Okay, so now I've got an A naught, B naught. And now I want to go and I want to OR those two guys together. So I'm going to go and invert the signal and send it into a NAND, and that would be it, X. So I've designed it. Now I look at it and I say, well, you know, right here I have two inverters, and right here I have two inverters. So I could redraw this guy A, B, A, B, and I could do that, and I could do this, and I could send them through there, and then I could send these guys through here, and I would get the same thing, would I not?
Can you
And,
also send the bottom AB just through a regular NAND?
I could, the bottom AB, no.
Are you supposed to connect those A wires and B wires on the bluish?
Oh yeah, they're connected. That's why I'm calling them A and B, so I don't have to connect them. Okay, so the issue is, no. See, if I send A and B through a NAND, what do I get? I get A, B, NAND like that, and that's not what I'm looking for. Okay, so now the issue is, does this circuit do what I want it to do? This is A, B, naughted, A naught, B naught, A naught, B naught, naughted, A, B, naughted, A naught, B naught, naughted, the whole thing's naughted. Okay, so that's what I've got. So I've got A, B, double naught, or A naught, B naught, naughted, naughted, A, B, or A naught, B naught. I hope I'm looking for an exclusive NOR. Am I looking for an exclusive NOR? Yes, I am. Woo-hoo! Yay. So I did it.
So pretty complicated right now.
Isn't that great?
No.
So, to get to here would be good enough. To recognize that I have inverters following each other would be the next step. So you may not want to take that next step quite yet.
So both of those are correct, one just uses more
Yes.
NAND than the other.
Yeah.
That's cheating.
With the one on the bottom, like, if you put the NAND first and then just put an inverter after it, that'd be alright?
No.
Like the bottom
So here
AB,
got
go
A,
into
B.
the NAND,
So I'm going to do that, and you
then
want an
the
inverter
after it.
after it. So what I'm going to
And then
get
it goes up to the other one.
is I'm going to have A, B naughted. I'm going to have A, B double naughted, which is AB.
And then you send it up to that last one.
But if I send it up to that guy, then I'm going to have that AB coming into this guy, and I'm going to end up with AB naughted.
And then when that other AB, by the time it goes through the AB double knotted,
On this side here, you mean? Yeah, no, I can't do that.
If you get it, let me know.
Yeah,
Show me.
yeah. Yeah, there's many ways you can do it wrong. Yeah,
But I mean, like, because if that's on the bottom, and the AB on the top, so then you have the AB knot going to that second man, with AB going to the second man. And then by the time it gets through, don't you have AB double knotted and AB knotted, which is just AB and AB knot.
You get the AB knot, the double knot makes it AB again, so it's basically just like you wrote about it. They're going to invert, the knots will turn to ABs, the ABs will turn to knots. I just don't know where it gets the and or the or.
okay.
It's friggin' and up there. It's not.
Now, we remembered from chapter 4 or 5, one of the others, that if I have NORs and I want an inverter, I do this. And if I have NANDs. If I have NANDs and I want an inverter, I do that. If I have NANDs and I want an AND, I do this. If I have NANDs and I want an OR, I do that. So if in a previous chapter, we talked about NAND being a universal gate. If I want an inverter, I do that. If I want an AND, I do that. If I want an OR, I do that. If I have NORs and I want an inverter, I do this. If I have NORs and I want an AND, we gotta hook those guys together, I do this. And if I have NORs and I want an OR, I do that. So that is where I got the groups of symbols that I used when I brought them over to the other side to get what I wanted. So I wanted A and B or A naught, B naught. That's what I'm looking for. So A and B, I do that. I need A naught, so I get an A naught. I need a B naught, I get a B naught. And then I need an AND to put them together, so I do that. Then they're ORed together, so I use the combination that gives me the OR. And that's how I get from one to the other. So if you don't have that at the top of your list of things in your memory, you write it down and then use it. How do I make an OR out of a NOR? How do I do that? All right, 6-6. What's the next one? 6-12. Wasn't 6-12 too hard? No, 6-12 is not too hard. Okay. Figure below shows another design for a 4-bit parity generator. Determine if the circuit's going to work at all, and if it's even or odd parity. Okay, so I got the least significant bit, the next bit, the next bit, and the last bit, most significant bit. And I'm going to go and bring these two guys in to an exclusive OR. And then I'm going to bring this guy into that next exclusive OR. And then I'm going to bring that guy into an exclusive OR. And I'm going to say this is my parity bit. Okay, so we take something. 1, 0, 1, 0. If I have even parity, I should get a 0 out. If I have odd parity, I should get a 1 out. Okay? The 1 and 0 gives me a 1. The 1 and 1 gives me a 0. The 0 and 0 gives me a 0. I probably have even parity. Do it again. 1, 1, 1, 0. The 1 and 1 gives me a 0. The 0 and 1 gives me a 1. The 1 and 1 gives me a 1. 1, 2, 3, I have even parity. So this is something that's gonna, I could check the other what? 5 combinations? No, there are 14 combinations, right? There's 16 possibilities. But I got 2 of them. Both times I got that this is giving me even parity. I'm going to call it an even parity generator. Okay, so if we quit there, that gives us enough time on Thursday to finish the homework and to do the study guide, and then be ready for the test on next week, Tuesday. Okay? Good enough?
You said on Tuesday, Dan?
Yes. Yeah. Unless you want it earlier.
I'm okay with